Welcome back to grade 9 Applied Mathematics. We're continuing our work in Unit 6, which is really applications of linear relations. Today's lesson is called Talking About Lines. This is lesson 4, and we're going to look at 4 specific applications of lines. And just a reminder that when we're talking about a line, slope and rate of change are synonymous and interchangeable. The y-intercept and initial condition, they are interchangeable. That's where your line intersects the y-axis. It's the y-coordinate of where that happens. We've already discussed that y equals mx plus b is the equation of a line. M is your slope, b is your y-intercept. Given an independent/dependent value, you can determine the corresponding dependent or independent value by using one of 3 things: the equation of the line, the graph. You could also use a table of values. You'll see that we're going to be looking at that as well. Remember, a direct variation passes through the point 0, 0, or the origin, and a partial variation does not. So if we were meeting face-to-face, you'd have your class note in front of you, and hopefully you have that open right now. And we would walk through the first example together, and then you would be given time to do the rest of them. So let's just start by taking a look at the very first question. So the first one was called happening height. It says a sunflower seed is planted. Jill monitors its growth. She notices that the plant grows by 2.5 centimeters every week. Now remember, it started from a seed, so you can make an inference about what that initial height should be. And what I'm going to get you to do now is I'm going to get you to fill in this table of values, and it will be our first time to ponder pause. All right, so resuming, the initial height should be 0, and every week it says it grows by 2.5 centimeters, so notice how that pattern will keep repeating. Up 1 week, up 2.5. I'll just do one more, and then you'll get the idea. Up another week, and the height of the plant goes up by 2.5. So if you filled your table in correctly, it'll then jump to 7.5 after, well, let's do them all. 0 plus 2.5 to 2.5 plus 2.5 to 5 plus 2.5 to 7.5 plus 2.5 to 10 and plus 2.5 to 12.5. But you got to be careful and look over here, because sometimes these might jump by a value other than 1. In this case, they don't, so these values are correct. All right, the next thing you're going to need to do is graph this data and draw the line of best fit. So you've got your note open in front of you, graph it, and then draw a line through it. Best to use a ruler when you draw the line. Again, a time to ponder pause. All right, resuming to take this up. So notice I plotted all the points. You could probably do it this way. Plot the point 0, 0. Put a little check mark there. This is the point 1, 2.5. That's the point 2 over 5 up. 3 over 7.5. Notice the scale here. This is 2.5. You might want to write in the ones that are missing 7.5. This one is 12.5. So that's the point 3, 7.5. There's the point 4, 10. 4, 10. And the last one I plotted is 5, 12.5. All right, so what you're going to do now is figure out what's the slope of the line. I'd like you to do that from the graph. You draw a right triangle, whether you want to draw this right triangle, whether you want to draw a bigger right triangle, I'll leave it up to you, but make sure you look at the scale. Use your right triangle to find the slope and compare it to the rate of change. And again, a time to ponder pause. All right, resuming to take this up. So in the right triangle, I'm going to draw right here. We can see that this is 1. And we can see that that is 2.5. So slope is going to be rise, which is 2.5, over run, which is 1. So 2.5 over 1, that gives me 2.5. Now what will my units be? We did the rise, and remember the rise is measured in centimeters, so I could put centimeters here. And time is measured in weeks, so I could put 1 week here. So what I'm really doing is dividing 2.5 centimeters by 1 week, and that would give me units. Because this is in context, so the rate will have units when you divide them and find the slope. It's 2.5 centimeters per week. And that is exactly the same information we were given over here. It grows by 2.5 centimeters every week. All right, that was the slope calculation. What you're going to do now is find the y-intercept and talk about how that relates to this context of a sunflower seed. And again, a time to ponder pause. Resuming to take this one up, and we can see the y-intercept is right here. It's the y-coordinate of where we cross the y-axis, and we're crossing the y-axis at 0, or we're passing through the origin. So the y-intercept is 0, and it is the initial height of the plant. Now, given that this was a seed, it makes sense for the initial height to be 0 because the plant hasn't even grown yet. All right, now testing what you remember. Can you come up with an equation? And in this equation, notice this is height. So let's use the variable h for height for the dependent variable. Let's use the variable t for time for the independent variable. Use your slope and y-intercept to come up with the equation. And again, a time to ponder pause. All right, resuming to take this one up. So the equation we're going to use is h is equal to, then we will put our m times our independent variable, which was t, plus b. So normally we write y equals mx plus b, but we talked about in context you should always use meaningful variables, and in this context our independent variable is time, so variable t, our dependent variable is height, so the variable h. So h equals 2.5 because that's the slope, t, we could put plus 0 because that was our initial condition, but in the end that's just going to simplify to h is 2.5t. All right, there's our equation. All right, let's move forward. Use both the graph and the equation to find the height of the plant at 8 weeks. And also, when will the plant have a height of 25 centimeters? And again, a time to ponder pause. All right, so resuming and taking this up. All right, let's move forward. So we talked about when you're going to use the graph, you should use guidelines. So I got this 20 here. By drawing these blue guidelines. So let me just change this to blue. So I drew my blue guideline. I went to 8 weeks, draw a vertical line. This is where it hit the graph. Draw a horizontal line coming over to there, and I can now see that would be 20 centimeters. Make sure that when you're making a prediction by, in this case we're extrapolating, using the graph you have to draw your guidelines. Using the equation is h is equal to 2.5 times t. Time is 8 weeks, so we're just going to write h is equal to 2.5 times 8, and that gives us 20. When will the plant have a height of 25 centimeters? So I drew a green guideline, came up to 25, horizontal line over to the curve, and then I draw a vertical line down to make my prediction, and I can see that would be 10. So I've done this using green guidelines, and again, whenever you're using the graph, please make sure you draw your guidelines. So I now know that was 10 weeks. To use the equation, its height is equal to 2.5 times t. This is definitely an h. Guess I didn't mention that before, but we knew that was a t, so we plugged that in for t. So I'm going to plug in 25 for h. 25 is equal to 2.5t. I'm going to have to undo this, so the operation between the 2.5 and the t is multiplication. So I will divide by 2.5 to undo that. 25 divided by 2.5 is t, and t is 10. So it doesn't matter whether I use the graph or the equation, they both give me the same answer. All right, moving forward to the next page. Explain whether we're going to continue making predictions. So there's a prediction at 6 weeks, one at 20 weeks, and one at 45. You're going to think about whether it's best to use the graph, which is right here, the table of values, which is right here, or the equation to make your predictions. So think about for each number that's down there, is it appropriate to use the table of values? Could we do it? Could we use the graph? Or can we use the equation? Again, a time to ponder pause. All right, so resuming to take this up. So if we wanted to use the table, the first thing I'm going to have to do is I'm going to have to add another row. So plus 1 plus 2.5. So it's possible to use the table, but I'd have to add another row. We could easily use the graph because I can come up to 6 and draw my guideline. This is not going to be very straight. And then I could come across like that, and I could see 50. So it's possible because at least 6 weeks is visible on the graph. And of course I could use the equation always because I'm just going to do 2.5 times whatever the time happens to be. In this case it would be 6, also going to give me 50. Now we have a problem when we go to the 20-week mark, because if we're going to use the table, technically we are going to have to add 15 rows to get out to week 20. I suppose you could use different patterns in the table and now figure out what a 5-week jump would be. So if you jump by 5 weeks, you would get 12.5 over here. So maybe you could add groups now to go from 5 to 10 to 15 to 20, and then you do 3 jumps, but each time it would be 12.5. But I still think that would be a bit challenging. The graph, we're not going to really be able to use at all because we're not going to be able to accurately extend this all the way out to 20 and then extend that out. There certainly is no room vertically to extend this up. There might be room horizontally, but no room vertically. So I'm not going to be able to use the graph at all. Possible to use the table, but that's a lot of extension. Always can use the equation. So I think in this case, I would rather use the equation h equals 2.5 times 20. And when we come to 45 weeks, we are just exacerbating or making the problem a bit worse because now, obviously, I can't use the graph because I don't have enough horizontal space to extend this to 4.5 times its length. And there certainly is no vertical space to extend that by 4.5. I would now have to add an additional 40 rows in here, but we did talk about, maybe instead of extending by 1, we could jump by groups of 5. But that would still be 8 jumps by those groups of 5. So I'm going to say the table is probably not a good idea to use. Again, in this case, I'd rather use the equation. So once you have the equation, I think it's probably going to be the best for making predictions, especially for large numbers that are not in the table, nor are they on the graph. All right, next slide. You're going to decide if this is a direct or partial variation, with a bit of an explanation, and then talk about what type of correlation it has with a bit of an explanation. Again, a time to ponder pause. All right, resuming to take this up. This clearly passes through the origin, so it's a direct variation. We can see that here. We can also see that here. And of course, we can see here that this is just a constant times or a multiplier times our independent variable. There's nothing being added here, or we note plus 0. So all of these are the forms that we need to have to be a direct variation. This is a direct variation. It has positive correlation because as time increases, height increases. So I just noted positive correlation since both time and height increase together. All right, so that would be how we would have filled in that very first page. We've answered every single question for happening height. I'm just going to pause for a second. All right, so I just wanted to show you, we filled in answered all of the questions on this particular page. I guess the only one we didn't answer is this one right here. If the height were to grow at a rate of 3 centimeters per week, what impact would that have on the graph? So I'm going to get you to think about that now, and then I'll discuss that one with you. So let's pause. All right, so resuming after you had some time to think about that, this rate 3 centimeters per week here, I'm not going to be able to write on this because this is a PDF document. It's 3 centimeters per week. Before it was 2.5 centimeters per week. So the rate has increased in magnitude. That's going to make it steeper. So before we went over 1 and up 2.5 and we were here, now we're going to go over 1 and up something a little bit greater. That'll put us up here. We're going to get a line that's steeper. So what will happen here is the impact it will have on the graph. The slope is going to change. The slope will be greater, so the line will be steeper, but it is still going to pass through the origin because we still started by planting a seed. All right, so now what you would do on your own is there are 3 more activities to go. There's disappearing depth, there is pizza with pizzazz, and there is fence post. Now, if we were meeting face-to-face, then what would happen is I would be circulating, answering any questions you have. So what I'm going to do is I'm going to post the full solutions to these 3 extra activities, pages 2 to 4, and then you can check there. You can contact me if you have questions. And then we have more practice with these types of relationships, kind of an EQAO sampler, questions that might, but EQAO, you have to remember, is also part of the content. So just because it says it's an EQAO sampler and it came from EQAO, EQAO covers our curriculum. So these are things you need to know. So just some practice. See if you can answer these multiple choice questions, and again, the solutions will be posted. So that brings us to the end of lesson 4, talking about lines, sort of putting it all together and seeing what we remember. If you've made it to the end of the video, once again, thank you for watching. Don't forget to like and subscribe. And as always, take care and stay safe.